Good morning, students.
Good morning.
Okay, let us start today's class. We have almost 50% of population. Okay, let me consider a matrix A. We'll start a new thing today. Consider a matrix A. 1, 4, -1, 0, 2, 1, 0, 0, 3. And consider few vectors. x1 is equal to 4, 1, 0. x2 3, 2, 2. x3 3, 0, 0. Okay. Now let us multiply ax1, ax2, ax3. How much they become? 3 cross 3 multiplied by 3 cross 1. The result is again 3 cross 1. So in each of these cases, so what is the result? The first one, 1 4 minus 1 times 4 1 0. 4 plus 4, that is 8. The next one is 0 actually. So 8. Then you have 0 times 4, 2 times 1, 1 times 0, that is 2. Then you have 0. Here comes another one, ax2. So 3 plus 8 minus 2. 3 plus 8, 11 minus 2 is 9. Then it comes to the chair 6. Then next one is also 6. Come to the last one. This is 3 0 0. Now, what do you observe from all these three? Can I write this one as 2 times x1? Can I write this one as 3 times x2? Can I write this one as 1 times x1? x3, sorry, 1 times x3, right? So here is an example that tells whenever we are multiplying a matrix A with a vector x1, the result is a scalar times the vector x1. So multiplying the matrix A with any of these vector x1, x2, x3 is nothing but multiplying the vector by a scalar quantity. Well, the scalar quantity is not a random value. It has to be chosen very suitably. But then that is what the matrix multiplication talks about. Okay. And this example gives rise to one of the very powerful concept called as eigenvalues and eigenvectors. Just a minute. Okay. So it's better I'll write the definition. Okay, here we have some keywords. Eigen. Eigen is one of the keyword here. And from eigen, you have eigenvector. Eigen, it's actually a German word. The meaning of eigen is this, what is that? Characteristics. Characteristics. So you have you can have one eigenvector, but then the matrix has to be a square. It's a square matrix. Provided this equality satisfies, where A is the matrix, X is the eigenvector, lambda is the scalar quantity which we call it as eigenvalue. Okay, so in this example, we have x1, x2, x3 are the eigenvector, and 2, 3, 1 are the eigenvalues. But then there is also a possibility, something like this: A um, A times a zero vector is equal to lambda times zero vector. Here also the inequality satisfies, but this is not legitimate. This is not legitimate. Why? Because um, you cannot have eigenvector as zero vector. Zero vector as eigenvector. You cannot have zero vector as eigenvector. Eigenvector cannot be zero, but eigenvalues can be zero. So this is not accepted. This is not accepted. So let us see in another example and let us find something. Okay, we have mm, A is equal to 0, 5, 7, 0, -1, 2, 0, 3, 1. And a vector I have as 5, 0, 0. Can we ascertain that x is the eigenvector of A? Can we ascertain that x is the eigenvector of A? So for that, um, let us find out what is AX is. What is AX? The result of AX would be 0. This will also be 0. This will also be 0. This is your AX. So A times the eigenvector, so-called eigenvector, not yet proven. So A times the X vector is equal to 0, 0, 0. Well, I can very well write that this 0, 0, 0 is nothing but 0 times 5, 0, 0. So here I have lambda value is equal to 0 with lambda equal to 0. So lambda equal to 0 is a perfectly legitimate one. So Ix can be 5, 0, 0. That is also legitimate one, isn't it? So that is what. If A is this, X is this, it's proved that lambda equal to, with lambda value is equal to 0, this can be one of the eigenvector. Let's take another example. What happened? So here also let us check whether it is an eigenvector or not. Ax is equal to 2 plus 1, that is equal to 3, and 7. But then here we don't find 3, 7 to be any multiple of the vector 1, 1, right? Say that is, we want this 3, 7 to be a multiple of lambda times 1, 1, which is actually appears to be impossible, which it appears to be impossible in the sense that the first value is lambda, yes, first value is 1, second value is 1, So first value becomes lambda, second value becomes 1. I mean, both the values becomes equal. But here you have 3 and 7 unequal values. So that makes little bit tricky. It may not, it is not feasible. So this is not one of the eigenvector of the matrix A. Okay. Now let us further our discussion a little bit. Okay, we have been writing um, we have been writing that Ax is equal to lambda x. This I can write it as Ax minus lambda x equal to 0. This further I can write, if I take x common, A minus lambda times x is equal to 0. Now, did I write it correctly? No. The reason is A minus lambda. A is a matrix, lambda is a scalar quantity, a single value. So, dimensionally, these two are not compatible. So, what I'll do here, I'll put here identity matrix so that whenever I take x out of it, so it's still 1 and I'm multiplying with that. So here comes A minus lambda I times x is equal to 0. Now if I write A minus lambda I as B and this becomes x, so this is same as the very first equation that we saw in our very first lecture, Ax equal to 0. So nothing changes. The earth is round. Again, we came back to the same position. Okay. So uh, it's the same thing in a linear homogeneous system of equations. You are going to solve for x. The unknown is x. And of course, if b has an inverse, then we can solve this equation. And but then x is an eigenvector, right? X is an eigenvector. And we are saying that b is having an inverse. It's something like, let me write it. X is equal to b inverse 0. X equal to b inverse 0. And this, I mean, you can solve for x only when b inverse exists, right? Or I can write that x is equal to 0. If b inverse exists, that means x is equal to 0. But this is something contradictory. Eigenvector cannot be 0. Eigenvector cannot be 0. isn't it? So if we accept that eigenvector cannot be 0, that means B inverse should not exist. Hence, B inverse doesn't exist. If B inverse doesn't exist, what does that mean? B inverse, the square matrix B, this doesn't have an inverse. What does it mean? It means that the determinant of B is equal to 0. Determinant of B is equal to 0. Or in other words, determinant of A minus lambda I is equal to 0. So X will be an eigenvector of A. X will be an eigenvector of A if and only if this inequality holds. A minus lambda I, this equality holds, becomes 0. And this is what we call it as characteristics equation. And the roots of this equation tells the eigenvalue. Okay. So we have, let us say, take an example. Again, the same example I'll take. A is equal to 1, 2, 3, 4. So A minus lambda I is equal to 1, 2, 3, 4 minus lambda times 1, 0, 0, 1. So that I can write it as 1, 2, 3, 4 minus lambda 0, 0, lambda, and that is nothing but 1 minus lambda, 2, 3, 4 minus lambda. And its determinant if you find, you have 1 minus lambda times 4 minus lambda right, minus 6. Can you get the equation? I mean, can you get the roots? How much it would be? This is 4, 4 lambda minus lambda, minus 4 lambda, minus lambda, minus 5 lambda, plus lambda square, minus 6. So you have, lambda is equal to minus b. So this becomes plus b, plus minus b square is minus 4ac, 20 minus 4 plus 8 by 2a. So you have 5 plus minus 33 square root by 2. So these are the two lambdas you have. Okay, let's see another example. A is equal to t, 2t, 2t minus t. So a minus lambda I, a minus lambda I would be t minus lambda, and this becomes minus t minus lambda. This doesn't change. This doesn't change. Okay. So determinant of a minus lambda I becomes t minus lambda if I take minus common, this becomes t plus lambda minus 4t square. So this one becomes a plus b into a minus b a square minus b square minus t square minus lambda square minus 4t square. So this becomes lambda square minus 5t square. So if lambda square minus 5t square becomes 0, find out what is lambda is. That's a simple one. Lambda is equal to, you have two lambdas plus minus square root of 5t square. So let me write lambda 1 as square root of 5 times t, and lambda 2 is equal to minus square root of 5 times t. Now, what it signifies actually? It gives rise to some one important property which you will be actually utilizing in the subsequent classes. The important thing is, please notice that if the matrix A is uh, is parameterized, if matrix A is parameterized with a parameter t, then their eigenvalues are also parameterized with the parameter t. Eigenvalues are also parameterized with the eigenvalues t. If matrix A depends on t, so the eigenvalues depends on t. That is what the outcome is. Okay, we'll take one last example for today's class, then we'll wind up. Let us take A is equal to, now let us take 3 cross 3 and up 2 cross 2. 2 minus 1, 1, 3 minus 2, 1, 0, 0, 1. So A minus lambda I is equal to, here what happens? Like the two 2 cross 2 matrix case. Here in 3 cross 3 also, all diagonal elements are subtracted by the scalar quantity lambda. So we have 2 minus lambda, we have minus 2 minus lambda, we have 1 minus lambda. Rest of the values doesn't change. And what is determinant of A minus lambda I? Yeah, this is 0, right? 0, 0, 1 minus lambda. It's better to take this one as our row. Yeah. So this becomes 1 minus lambda. Mhm. I think I made a mistake. This minus will be common actually. So 4, oh, sorry, minus 4 plus lambda square plus 3. So this is actually 1 minus lambda times lambda square minus 1. Yeah, that's correct. And this is equal to 0. So we have lambda is equal to 1, lambda 1, let us say. Lambda 2 is equal to 1, lambda 3 is equal to minus 1. That is lambda equal to 1 from this equation, and lambda equal to plus minus square root of 1 from this equation. Okay, that's it. So we talked about eigenvalues today. Eigenvalues, eigenvector we started with, and we talked about the characteristics equation, and we started, we then continued on finding the roots of the characteristics equation, that is the eigenvalues. So we'll stop with this today. Next class we'll be talking more about eigenvectors and some of the applications that you will actually be utilizing in your thesis work. Okay, so that's all for today. Thank you.